We're going to talk about characterizing soil variability. When we talk about managing mineral nutrients, soil testing is the most important step in proper nutrient management, especially for phosphorus, potassium, and lime. Typically, we don't soil test for nitrogen in a lot of parts of the world, although more arid parts there are soil tests for nitrogen. There are other components, though, to nutrient management: nutrient source, application rate, application method, and application timing. But soil testing provides that guidance on proper amount of lime and fertilizer. It can be used to diagnose some deficiencies or toxicities. It can limit pollution. It can save money, can optimize plant health. And, for diagnosis, you might sample inside and outside of a bad area. If we look at this picture here, how many of you know what nutrient deficiency that is in the soybeans there? That's potassium deficiency, and we identified that from sampling inside and outside of the bad area. So how do we sample? Interpretation and recommendations for most crops are based on a calibrated furrow slice, right? So what depth? Well, they're calibrated to different depths for different situations, and you would have to talk to your soil testing lab, the university, or wherever you're getting your recommendations from and ask them, for this crop in this situation, what depth should I be using? Typically for pastures, we're looking at a shallower sample, around 4 inches. Tilled areas, that furrow slice, 6 to 8 inches. And established areas like lawns or so forth, 2 to 4 inches. Trees, shrubs, forestry, you might go deeper to 6 inches. The soil properties tend to be stratified, particularly in a no-till situation. So that's why we go for that shallower sample. When samples are collected to a shallow or too deep of a depth, the results can be skewed. So you want to make sure you're following the recommendations as far as depth. This is an example of traditional soil sampling. You're going to go to each one of these spots, zigzag your way across the field, and collect multiple cores and put them in a bag. And you might, if it's a large field, split it up into 2 or 3 different areas. Sample maybe a 20-acre area, and that represents one sample from that field. In precision ag, we're not trying to provide that average nutrient status like we are in traditional setting. We're trying to get that field variability, break that field up into smaller management zones. And there's a couple of ways we can do that. We can do grid sampling, and that can be grid point or grid cell sampling. And this is particularly useful when previous management has altered the soil nutrient levels. And that's something you can't see visually. You maybe have a new piece of land you haven't sampled before, and there's an old farmstead with an area that had a lot of livestock manure applied historically. Maybe several small fields were combined into one larger field, and so you want to characterize that variability. And so you can make a dense nutrient map that you could use for several years out. So you don't necessarily have to grid sample every year. Do it once up front to get that variability, and then decide how intensively you have to sample in the future. The other is directed, or often called zone sampling, and you have to have other data available, like yield maps, remote sense images, maybe a map from an EC cart that you've pulled across the field. You have to have experience with the field so you know where to direct your sampling, where to put the zones. And then there's some equipment considerations as well, because some equipment is going to require some grid-based information. You have to understand that fertility isn't the only source of variability, and so those are the kind of physical features or natural features that we might want to look at with zone sampling. And you can also combine both and do a grid sampling within a zone sampling. The difference between grid point and grid cell is with grid point, you lay your grid on the field and you take multiple cores around that point where the lines in the grid intersect. You put them into one bag for a sample. With the grid cell, when you lay the grid, you zigzag like you would in a normal field through that cell before you move on to the next cell. So when you're developing zones, one of the first things I recommend looking at is that soil texture. So now with Web Soil Survey, we have easy access to digital soil texture data. Soil texture does often result in some sort of yield variability, but you got to understand what about the texture is causing yield variability. You should ask yourself that, look into what texture you have, and how is it causing that yield variability. Is it the nutrient quantity? Is there some nutrient quantity issues out there causing yield variability? Nutrient intensity, for example, with phosphorus, you may have plenty of phosphorus, your liming's not quite up to par, and so that phosphorus isn't available. Is the soil moisture? Because, for example, a soil with more clays might be a little wetter, and then if you have a little more sand in an area, that's going to be a drier area in the field. As precision ag has developed, we've become reliant on yield mapping as a major tool. And we look at these yield potential zones, and then often we want a soil sample based on these yield potential zones. But I would recommend that you really need to understand that zone and what's causing that yield variability. Can we manage that yield variability? Is it something that nutrients are going to help with, or do we need to look at something else? What's our objective? How does pH and nutrient concentration, like P and K or N availability, influence that yield? And how does the yield influence nutrient requirement? Because these two are interrelated. Do we soil sample based on these zones, or is it a nitrogen issue where that soil sample isn't going to be as important? So let's talk about some of the input data that we can use to develop some zones. So historically, soil maps were developed based off of aerial photos, as we see here. We can go in now with electromagnetic sensors. They're commercially available, and we can develop a more precise soil map showing these zones. And we can use this in conjunction with other data to kind of delineate or designate these management zones. So this is an EC map that was generated by Dr. Grisso at Virginia Tech. And this is the shallow readings, the top 12 inches taken with a Veris EC meter. And EC generally relates to soil texture. The lower the EC reading, the coarser the texture, like a sand. The higher the EC reading, the finer the texture, like a clay. So we can see in this field that we have some sandy areas and we have some silty to clayey areas in that field. So then we can combine these data layers. Here you can see that we have the EC overlaid on the soil texture map, and we see that they align pretty well, but the EC readings obviously give us a more precise delineation of those soil zones, but the map helps us understand what those EC readings actually mean. So how do we delineate the zones if we have an EC map? There's actually two ways, and it's important to understand. Oftentimes we're sending this data out to a third party to map the data that we've generated. But I find often we don't know how they mapped it, and it makes a big difference. As we see here in this example, it's an equal range. And so what that means is that in between each color change, we have an equal range on the EC scale. So we go from 1 to 3, 3 to 5, in steps of 2. And we can see that this map looks very different than this map, which is equal distribution. And equal distribution often makes a better looking map. And that's why typically this is what is done. And we take and put the same number of colored pixels within each range. So we try and get this equivalent acreage under each color grouping. But if that map has real practical meaning, does equal distribution really work? Because now we're grouping different soil textures together just to get a better looking image. Here's an example of a Veris image used using equal range categories to develop the map. And we've delineated some zones using the equal range method laid over top of the soil zones. And what's interesting in this example here is if you look at these lines from the soil map, you can see that they don't quite overlay perfectly on what the Veris was seeing. So the Veris was probably picking up on some soil moisture issues in this field, or the soil map wasn't really that precise. And so in this example, we would go back out and do some soil sampling in these zones to confirm what we found with the Veris or confirm what's in the soil map. So in summary, yield zones might make sense under a maintenance strategy, as long as you understand the source of the yield variability. Grid sampling will provide more detailed information. A level of detail that is needed to gain advantage can be expensive. You're going to have to sample very intensively. And zone sampling requires that you understand the zones, the input data layers, and why they were generated and how they were generated.